Example 2, optimize using the method of corners. So this problem says we're going to maximize. And that first thing right there is called the objective function. All right, z equals. Notice the only one that has an equals, that one's called the objective function. We don't graph that one. Okay, do not graph that one. We are going to use that one at the end. So pretty much don't even look at that thing until the very end. All right, but the subject to, those are called the constraints. Okay, subject to, those are called the constraints. Think about what that word means. It's like boundaries. Okay, those are our boundaries. That's going to make our shape, our triangle, our quadrilateral, or whatever other shape it could possibly be. Okay, so I like the intercepts method. So if you look at the top constraint, okay, the X-intercept, I'd cover up Y, make Y equal 0. Okay, so then I'd have 2x equals 4. X has to equal 2. So the first one has an X-intercept of 2. You can go ahead and put a dot there on 2. And the first one has a Y-intercept. Cover up the X. X goes to 0. If X is 0, Y is 4. So we'd have a Y-intercept at 4. So we've got those 2 dots right there. Okay. So you should be able to make a line through that. If you want, you can kind of extrapolate the slope. And if I go down 4 and right 2 and down 4 and right 2, I'd have another dot there. And down 4 and right 2, I'd have another dot there. Or up 4 and left 2, if you want. I mean, you can do more dots if you want. Okay, can you even see those dots? Let me try to use my line tool and see if I can make it look even better. Do I have a line tool? That's not bad. That's not bad right there. Okay. So notice this one says less than. So I'm going to be shading down. Okay. You're going to be shading down. I would save it. Okay. I would save it and do that later though. Okay. Now let's look at the other line, the next line. If I wanted to find the X-intercept of that second inequality, I would let Y equal 0. Basically, I'm making a table of values and plugging in zeros, okay? But if I plugged in Y was 0, I'd have negative X equals 4. So that means the X-intercept must be negative 4. So 1, 2, 3, 4. There's going to be a dot right there, okay? For the Y-intercept, you let X equal 0. I would see 2Y equals 4. So then Y must equal 2. So Y equals 2. There's going to be a dot right there. Okay. Now, again, if you want to, you can extrapolate the slope. It looks like we go up 2 and right 4. So if I go up 2 and right 4, I'd have another dot there. And up 2 and right 4, I'd have another dot there. Or down 2 and left 4. Okay. So we can see what that looks like. And we can draw a line through. As for the shading, I can see less than, okay? So typically that means to shade down. Now, sometimes negatives throw me off, okay? But a negative here doesn't cause me any problems. It's a negative here. Remember, okay, when you have to divide by a negative in an inequality, you have to flip the symbol, okay? So that's where you're going to run into troubles. So if you're confused, if there's a lot of negatives, you might be better off to use slope-intercept form and put that in slope-intercept form. So by that, I mean I could do negative 2x or negative x plus 2y is less than or equal 4. I could add the x over, so 2y is less than or equal x plus 4. Divide by 2, you're going to get y is less than or equal 1/2 x plus 2. So you could always put it in slope-intercept form and graph it that way. Okay, sometimes people get less confused by doing it that way, but I think it's more work, so I don't really want to do it that way. But now if you think about it, I'm going to end up shading down from both of those two lines. Okay, now X is greater than or equal 0 is just a vertical line. X equals 0 is a vertical line, but greater than tells me I'm going to shade to the right. So down from both of the diagonal lines and to the right of the vertical line. Now, Y is greater than or equal 0. That's going to be a horizontal line. And I'm going to shade above. Okay. So notice we've kind of wedged in several different shapes. I see a triangle. I see a couple triangles, and I see a quadrilateral. Okay. But which of those shapes is the one that's down from both diagonals and to the right of the vertical and above the horizontal? You see which region I'm talking about? You should be shading inside this figure right there. I know it's kind of small. But that's it. Okay. Now, label the corners. There's a corner point, right? I can't do it. Pen's not wanting to work. Right there. Okay, and right there, and there, and there. So this one's easy. It's 0, 0. And this one's not bad right here. It is 2, 0. And this one right here is not too bad. That's 0, 2. But this one right here is going to be difficult because it's not right on a tick mark. Okay. So basically what you have to do is solve a system of equations. Okay. We're looking where the intersection. So go way back to Algebra 1 when we looked for where two lines crossed. Okay. Graphing was one way we could do that. We could graph it and look for where they cross, but this one's kind of hard to do. So you could do substitution, you could do elimination, or in this class we learned how to do Gauss-Jordan. Okay, you could do a Gauss-Jordan. You take these two, set them up as a system of equations because we don't care about the inequalities right now, and do a Gauss-Jordan. Or honestly, probably the easiest thing to do is do it on Desmos. Okay, so let's check out what it would look like on Desmos. So that top line was 2x plus y is less than or equal 4. And then the second line was negative x plus 2y is less than or equal 4. Okay. So check it out. Okay. What I want to do is find this intersection point. Whoops. I'm going to find this intersection point right here. With Desmos, you can just click there. Okay. Notice I just clicked there and it shows me that that intersection point is 0.8, 2.4. Okay. 0.8, 2.4. That's easier even than the Gauss-Jordan site. You could plug that in and do a Gauss-Jordan on it. You could do substitution. You could do elimination. You could do a lot of different things to find that intersection point, but that's probably going to be the easiest. 0.8, 2.4. Okay, now I'm almost finished. I've done all of the hard work, okay? Remember earlier it said if there is an optimum value, it's at one of the corners. We haven't even done anything with, right here, the objective function. Oh my gosh, this thing. I don't want a line. This, okay? That's our objective function, and that's our last step. What we have to do is plug the corners into that objective function, okay? So let's get this up a little bit. And let's go to Okay, let's start at 0, 0. Basically, you're doing 3 times 0 plus 4 times 0. That's what this function says, okay? This function up at the top, the objective function right here, says we're going to go 3 times x plus 4 times y. So you do that, 3 times x plus 4 times y, and that's going to equal 0 here. 0. You do that for each of those 4 corners. So each of those corners. So the next one's going to be 3 times the x number is 2 plus 4 times the y number is 0. That's going to be 6 plus 0 equals 6. And over here, 3 times the x number plus 4 times the y number. That's 3 times 0 plus 4 times 2. That's 0 plus 8 is 8. And then the hard one, I guess, you've got 3 times the x number plus 4 times the y number. 3 times 0.8 plus 4 times 2.4. You can always use a calculator. 3 times 0.8 plus 4 times 2.4 is 12. Okay. So last thing we need to do is answer the question. It says maximize. So maximize just tells me, find the biggest number. That's it. Well, the biggest number is 12. So the maximum, you'd say max. Here's how I want you to write the answer. Max z equals 12 at 0.8, 2.4. I want that whole thing written as your answer. Okay. I'll go ahead and stop that one.